Welcome to this video on domain and range.
Let's consider domain and range as seen from a graphical interpretation. From a previous video, you'll recall that the domain is a collection of all input values in a function, and a range is the collection of all output values. Let's consider this example. Before we consider the domain and range of this function, I'd like to point out some features displayed graphically here in the function. First of all, the open circle. This open circle, when placed on a graph, represents that the function does not contain that point. So this function does not contain the point 3,2. Notice this arrow on the other end of the function. This arrow appears to be pointing upward, but it really has two implications. It not only represents that there are points in this graph that are infinitely high up, in a sense that the function goes up forever in that direction, if you will. But that arrow also implies that there are points that go infinitely far to the left. And while that arrow appears to be pointing more upward than it does leftward, the implication is that there's a, in some sense, forever upward and leftward motion to this graph. Now that we've analyzed the features of the symbols in the graph, let's talk about the domain. Now in a minute I'll show you the domain of this function. In other words, what are all the possible input values for this function? But before I can do that, I have to give you a frame of mind here. When answering questions about domain and range, one often has to have a conversation with oneself because there's no math procedure for finding the domain and range of a function displayed graphically. So listen in on my brain as I have this conversation with myself. So, I want the domain of this function, which is the collection of all inputs, or x values. Well, what x values are represented in this graph? Does this function contain a point that has an x value of 3? Well, no, it doesn't, as represented by the open circle. Does this function contain a point whose x value is 4, or 5, or 1,000,000? Well, no to all of those, because there are no points on this graph whose x-coordinates are 4 or 5 or anything higher than that. Does this graph contain a point whose x-coordinate is 2 or 1 or 0 or -1? Well, yes, it contains all those. Does this function contain a point whose x value is -1,000? Well, yes, it does, because of the forever leftward nature implied by the arrow in this graph. So by just considering what are all the possible x values in this graph, it's occurred to me that any x value represented in this shaded green arrow here is a possible input to this function. So in some sense, that shaded arrow represents the domain of this function. In other words, any number in there is a possible input. Well, that shaded region goes from -infinity on the x-axis all the way up to 3, but not including 3. In other words, there's a point on this graph whose x value is 2.999, but there is no point, because of the open circle, on this graph whose x value is 3. And therefore the domain is all numbers from -infinity through 3. And before we go on to range, it's worth pointing out that to answer a domain or range question, there is no mathematical procedure to follow. It's simply the result of a realization. By looking at this picture, I had the realization that all the points on this graph have x values between negative infinity up through and not including 3. And that realization led me to the domain that you see there. Now let's continue with this one example and talk about the range. Again, the range is all the possible outputs, or y values, of a function. So I have to have a similar conversation with myself to determine the range. Well, looking at the graph, what are all the possible y values? Does this function contain points whose y values are -1, -2, -3, -4, and -5? Well, yes, it does contain such points. But notice that this function, for example, does not contain points whose y values are -6, -7, or -1000. There simply aren't any points that low on this graph. Well, does this graph have points whose y values are +1000 or +1,000,000? Well, it does, because of the arrow. And so when I think about the range, it occurs to me, I have a realization, that any of the y values represented in this shaded green arrow are possible outputs to this function, but that nothing lower than -5 would be a possible output because there are no points there. And so I would say that the range of this function is all numbers from -5 through +infinity, including the number -5, which you'll see represented by the bracket, because this function actually has a point whose output is -5. By the way, it's the point 1, -5 at the bottom of this graph. Well, I'm done with this example, but I want to leave it up to juxtapose it with a similar example that has some slight different meanings. You'll notice these two examples look roughly the same, but a few things have been changed. Before we answer the domain and range, let's look at some features of this graph. This solid dot here represents that the function does in fact contain the point 32, unlike the previous function. And this arrow here, in conjunction with this dotted line here, which by the way is called an asymptote of a graph, and this video isn't about that specifically, but those two things together represent something slightly different than the arrow did on the first example. They represent that there is an infinite upward progression of this graph, if you think of it that way, but that there is not an infinite leftward progression of this graph, in the sense that the placement of that dotted line or asymptote there represents that there are no points on this graph to the left of that line. With that being said, let's consider the domain. The domain is all possible inputs. So here's this conversation I'll have with myself. Looking at this graph, I can see that all the possible inputs are between -2 and +3, inclusive of 3. In other words, there are no inputs below -2. There simply isn't any graph over there, as implied by the dotted line. And there are clearly no inputs to this function beyond +3, or to the right of 3. So I would express the domain as all numbers -2 through 3, including 3. Why including 3? Because there is a point on this graph whose x-coordinate is 3. Why not including -2? Well, the dotted line implies that there is no point on this graph on that line or to the left of it. Now let's consider the range of this function. The range is the same as the function on the left. This function contains outputs anywhere from and including -5 up to +infinity. Let's take a look at another example. Let's find the domain and range of this function. First, though, let me point out some features. This arrow here on the left side of the function seems to be getting closer and closer to the x-axis. Because it's drawn that way, the assumption here is that this graph goes infinitely far to the left, but never crosses that line. A function would never be drawn so close to the x-axis if that weren't the implication. So that has to have been the author's intent. On the right side here, just a reminder, this upward arrow, so to speak, is an indication of two things. One, that there are infinitely many points going upward on this graph, but that it also goes infinitely far to the right as well. So, with all that in mind, let's first talk about the domain. The domain is all possible inputs to this function. So let me have a conversation with myself here. Does this function have an input value of negative 1,000? Yes, somewhere far to the left there's a point whose x-coordinate is negative 1,000. Does this function have an input value of positive 1,000,000? Yes, somewhere far, far to the right there is a point on this graph whose x-coordinate is 1,000,000. And not only that, but it seems to me by looking at this graph that any x value or input I would choose, there is a point on this graph corresponding to that. In other words, any real number is a possible input to this graph. So I'm going to display my domain as all real numbers, or if I choose interval notation, negative infinity through infinity. Now let's consider the range. The range is all possible outputs. Here's my conversation with myself. Is there a point on this graph whose y-coordinate or output is 1,000 or 1,000,000? Well, yes, because of the forever upward nature of the graph. Is there a point on this graph whose output is negative 1,000,000 or even negative 1? No. If you look at this graph, there are no negative outputs whatsoever, or y values. Is there a point on this graph whose y-coordinate is 0? No, there isn't. By virtue of the fact that this graph appears to be drawn in such a way that it never touches the x-axis or intersects with it. So there's no point on this graph whose y-coordinate is 0. But wouldn't there be a point on this graph for any number above 0? For example, if I chose 0.0001, wouldn't there be a point on this graph that has that as its y-coordinate? Well, that seems to be the implication by the way it was drawn on the left. So I would say yes to that. And after having this conversation with myself, it occurs to me that any of the y values in this green shaded arrow correspond to an output on this graph. And therefore, I'm going to express the range as all numbers 0 through infinity. Notice I've used an open interval by excluding 0 because there is no point on this graph whose y-coordinate is 0, just anything above 0. Here's another example. This thing is called a step function for somewhat obvious reasons. Before I figure the domain and range of this function, which I could do simply by the picture, it's worth taking a brief excursion into where a step function would come from. So imagine you had a job where you're being paid for a task, and depending on how long that task took you, you would receive different pays. Instead of paying you hourly in the traditional sense, suppose you're being contracted to do a job, and if it takes under 2 hours, you're going to charge $40. If it takes between 2 and 4, including possibly 2 itself, you're going to charge $80. And if it takes between 4 and 6, you're going to charge $130. That kind of scenario in real life would lead to a step function. Your pay is a function of the amount of hours it takes you to complete the task. Now I didn't need that information to answer the domain and range, but it was just something worth looking at because step functions do occur in the real world. Back to the question of domain. Domain being all possible inputs, it appears to me just by looking at this graph, if the input is anything between 0 and 6, then there will be an output to this function, and so I'm going to list the domain as all numbers 0 through 6. But notice I've excluded 0 itself and included 6. You'll notice the open circle on the far left side of the graph means that this graph does not contain the point 0, 40. In terms of your job, in terms of that example, if that were part of this, that would mean that you don't get any pay. There's no issue of pay if you work 0 hours. Okay, as far as range goes, range is all possible outputs. There are only 3 possible outputs to this function: 40, 80, and 130. Any other y value than 40, 80, or 130 does not correspond to any points on this graph, and therefore the range is just those 3 numbers. Let's talk about the concept of implied domain. We'll get to that in a moment. First, let's consider the following 3 functions. Now, these functions appear to be the same, other than the fact that they have different names. One's called j, one's called k, and one's called m. For example, if I asked what j of 12 was, you would probably say 36, because j is the function that multiplies the input by 3. 12 times 3 is 36. Well, likewise, k of 12 is 36, and m of 12 is 36. And this shouldn't be surprising, it's just strange that I've named this function 3 different things, or so it would appear. Well, the point I'm getting at is that the domain of a function is all the possible inputs, and it would appear just on what's being shown here that any number could be an input to this function. Any number is multipliable by 3. If you were asked the domain of any of these functions, or if I were, I would say all real numbers to all of them if they weren't listed. But that's sort of my perspective as the reader of the function. What if I'm the author of the function? I'm the one creating it. What if in this first function in j of x, I wanted the domain to only have 2 numbers? For whatever reason. It would be strange, but as the author of the function, I'm allowed to state any domain I like. What if for k I decided the domain would be any integer? An integer, by the way, is basically a positive or negative whole number. Or what if I wanted the domain to be all real numbers, including decimals? Well, I can define the domain as the author of the function to be anything I like. So now that I've changed the domain of these functions, it would appear that they are different functions in some sense. They all involve multiplying the input by 3, but they all contain different points. Now at this point you might be thinking, how did he find these domains? Well, I didn't. I'm stating them. You see, in the previous problems, when we talked about domain, we were the reader of the function. We were being shown a function that was created by someone that wasn't us, and we were asked to find its domain. But I'm putting us in the position here of being the creator of the function. If I want to create 3 functions, all of which are multiplying by 3, but have different domains for all of them, I can create those. Now, that being said, in this first function, j of 12 is 36, obviously, because 12 times 3 is 36, but k of 12 and m of 12 are also 36, obviously for the same reasons. But now, consider j of x having an input of 5. If 5 is the input for j, what's the output? If you thought 15, you're wrong, because 5 is not a possible input per j because the author of this function didn't allow it. It's undefined or does not exist, which is what the DNE stands for. Why doesn't it exist? Because the only possible inputs to J are 12 or 100. So said the author of J. For K of 5 would be 15, because 5 is an integer and therefore an allowable input. M of 5 would also be 15 because 5 is a real number. Real numbers are basically all positive and negative whole numbers and decimals, very roughly stated. Well, we can see that for J of x, J of 2.1 wouldn't exist. We can't plug in 2.1 to a function where the author's not allowing us to. But notice that K of 2.1 also doesn't exist because the author of K restricted the domain to the integers. 2.1 is not an integer, therefore it can't be an input for K. And for M, 2.1 is a valid input because 2.1 is a real number, and M of 2.1 is 6.3, which by the way is 3 times 2.1. Now, I haven't told you yet what implied domain is. Implied domain is the domain that we are to assume the function has if the author neglects to state it. Here's a more formal definition. In other words, if a function is listed and as a formula and no domain is specified, the implied domain is assumed to be all real numbers that you could plug into that function as an input that would yield or lead to a real output. Now, why would an author of a function neglect to state the domain? Well, it happens quite a bit. And so we have this concept of implied domain. Here's an example. Consider f of x here. If I wanted to, I could say that the domain is only the numbers 1 and 3. As an author of this function, I could say you can only plug 1 or 3 into this function, and whatever output you get is the output, but there are only 2 points on this function. But quite often, we just state a function and we don't state the domain of it because it's implied that if we don't do so, that any real number that we can plug in and get a real number out is a valid input. Now, unfortunately, there's no procedure for finding the implied domain. One simply has to think to oneself, what numbers could I plug in for x? Can I plug in 1 for x? If I plug in 1, do I get a real answer? Well, yes, if I plug in 1 here, I get radical 6. That's some decimal, but it is a real number. Can I plug in 3 here? Absolutely. Because if I plug in 3, I get radical 4, which is 2, and that's a real number. Well, there's lots of numbers I can plug in, and there's lots of numbers I can't. And so finding the implied domain is really about ultimately finding out what inputs you can have that would lead to a real output. Now, there's no procedure here, but I'm going to share my thoughts that led me to the implied domain here. Watch my thought process as it unfolds. First thing that occurred to me is that the radicand can't be negative. The radicand is the thing under the radical, by the way, so the radicand in this problem is 7 minus x. But that can't work out to a negative number because then I'll have radical negative, which isn't real. It occurred to me that if x were a number higher than 7, let's say x were 8, or 10, or 1,000,000, that the radicand would be negative, and therefore the result wouldn't be real. And therefore I can't plug in 8, or 10, or 1,000,000, or anything like that, without and still get a real answer. So those numbers must not be in the domain. So it occurs to me that x can't be a number higher than 7 to get a real output. Therefore, there must be no numbers higher than 7 in the domain. It also occurred to me that I can have radical 0, can in fact have radical 0, and I can have radical of a positive number as well. And so if the radicand is 0 or positive, I would have a real output. Well, as long as x is lower than 7, look at the function and imagine x being 1 or 2 or 3. If x is lower than 7, I'm going to get a real output here because the radicand is going to be positive. If x is 7 itself, I'll get radical 0, which is 0, and that's a real number. And so 7 is also part of the domain. In fact, negative numbers are also part of the domain. Imagine x being negative 1,000,000. Wouldn't I then have radical of positive 1,000,007? That's a real number. So it occurred to me that x can in fact be any number 7 or lower. It just can't be higher than 7. Now notice I didn't apply a mathematical procedure here. I simply thought through what numbers x could and couldn't be, and I've now come to the conclusion that the domain, or the possible inputs, is the set of all x such that x is less than or equal to 7. By the way, you can also write this, and it's very common to write this using interval notation, which would be negative infinity through 7. Here's another example. Now there are no radicals here, so we don't have to worry about the radicand being negative, and therefore the function not being real valued. But we do have something else to think about here. We have a denominator. And whenever you have a denominator, you have to worry about x's that will make that denominator 0. So, for example, if x were 5, I recommend pausing the video here and plugging in x equals 5 to this formula. In other words, find g of 5 and hit play when you're ready. What you should have found there when you plugged in 5 for x is you should have gotten 1 over 0. But 1 divided by 0, or anything divided by 0, doesn't exist in the real numbers. And so x can't be 5 as an input to this function because it wouldn't give us a real output. But there's other numbers it can't be too. Let's proceed with my thought process here. So my thinking is, if the denominator is 0 for any given x, such as 5, then the function would not have an output. Now it turns out the denominator is 0 not only when x is 5, but also when x is negative 3, and you can see my algebra there. I essentially solved the equation denominator equals 0 to find out what x cannot be, or what inputs are not allowed. Therefore, x cannot be negative 3 or 5. That's my first conclusion. But it also occurs to me that as long as the denominator isn't 0, then the function would have a real output. But wait, how about x equals 4? Look at the top function there. If x is 4, is that an allowable input? Wouldn't that give me 0 over something? Yes, it would, but the denominator wouldn't be 0 in that case, and there's nothing wrong with the numerator being 0, so 4 is definitely part of the domain. In fact, any number that isn't negative 3 or 5 will give me a denominator that's not 0. And therefore x can be any number other than negative 3 or 5. Now again, there's no procedure here, just a sequence of thoughts that led me to the conclusion that x can be any number other than 5 or negative 3. So I can state my domain as the set of all x such that x isn't negative 3 and it isn't 5. By the way, this can also be expressed using interval notation. It looks strange, but what I'm essentially saying here is x can be anything negative infinity through negative 3, not including negative 3, or, as represented by the union symbol, any number negative 3 through 5, not including negative 3 or 5, or any number 5 through infinity. And while this may seem strange, it is sort of the traditional way of writing the domain of this function. Either one of those two is fine, though, as far as I'm concerned. Okay, before we go to the next problem, I just want to reiterate something about implied domain. If the author of this function, as originally written, had specified a domain, say they had said x is all numbers 10 or higher, and the author wanted that to be the domain, that would have been fine. That's their prerogative. The implied domain is really just us trying to get into the author's head when they don't state a domain. So any author who wrote this function, we would assume that they meant the domain to be all numbers except -3 or 5, because they didn't state a domain at all. This last problem is extremely difficult, and if you're confused by the prior two problems, you may want to just fast forward through this one. But if you're up for a challenge, listen in. Now, this problem contains two things that might cause a certain number not to be a valid input. It contains a denominator, as the last one did, but it also contains a radical, as the previous one did. And really, when it comes down to it in a math class, an implied domain question is going to have a denominator or a radical or both, because those are really the only interesting questions to ask about. If a function doesn't have a denominator and it doesn't have a radical, it really more than likely has an implied domain of all real numbers in almost all cases. It's because it's radicals and division by 0, or radicals of a negative and division by 0 are the two things primarily that make things non-real. Moving on with this very challenging problem, let me share my thought process. My first thought was, well, the radicand can't be negative. But if x is anything lower than 5, look at the denominator and imagine x being 1, 2, or 3, say. If x is anything lower than 5, the radicand is going to be negative, therefore h won't have a real output and those numbers aren't allowed. So x can't be any number lower than 5. How about 5 itself? Well, x could be 5. Look at the original function. If x were 5, we would have radical 0, which is 0, and then 4 minus 0, my denominator would be 4. There's no problem with x being 5 itself, it just can't be lower. But then I also started thinking about the denominator. If the denominator is 0, then the function is not going to have an output. I'm going to recommend pausing the video again and try to answer this question during the pause. What value of x would make that denominator 0? Hit pause and then play when you're ready. If you came up with x being 21 would make that denominator 0, then you have a very clever thought process, and I congratulate you on that. It does. You can see by my work here, if x were 21, the denominator would work out to 0, and therefore x can't be 21. Not because 21 would make the radicand negative, but because it would ultimately make the denominator 0. It also occurred to me that that's the only thing that would make the denominator 0, is if I had a 16 under that radical, aka if x were 21. So, after coming to the conclusion that x can't be 21, but also having prior come to the conclusion that x must be 5 or higher, my overall conclusion is that x can be any number 5 or higher except for 21. So there's two ways I could write that. I could say that the domain is the set of all x such that x is 5 through 21, not including 21, or higher than 21. I could also write this in interval notation. The first interval to the left of the union sign being 5 through 21, excluding 21 itself, and the second interval to the right of the union sign being all numbers higher than 21. And that completes the lesson on functions and this series on functions and function operations.